So let us continue. We'll start with mechanism of chymotrypsin action. So chymotrypsin, what does chymotrypsin do? It cleaves the peptide bond selectively on the carboxyl side of the large hydrophobic amino acids such as tryptophan, tyrosine, phenylalanine and methionine. Okay, so a big chain is there. And this chymotrypsin comes and cleaves from the carboxyl terminal side. Okay, and of large hydrophobic amino acids. We'll be taking hydrophobic amino acids like tryptophan, tyrosine, phenylalanine and methionine. Chymotrypsin is a good example for the use of covalent catalysis that we studied here. Covalent catalysis. What is happening in covalent catalysis? To increase the rate of acceleration through transient formation of catalytic substrate covalent bond. Okay, increase in rate acceleration. How? Because we are forming the transient formation of catalyst and substrate of covalent bonds. We are using covalent bonds here. So this is its example. The enzyme employs a powerful nucleophile to attack the unreactive carbonyl group atoms of the substrate. This nucleophile becomes covalently attached to the substrate briefly in the course of catalysis. Serine is the part of the catalytic triad that also includes histidine and aspartate. So serine, histidine and aspartate. 3D structure of the chymotrypsin reveal that this enzyme is roughly spherical and comprises 3 polypeptide chains linked by disulfide bonds. So in 3D structure, what we will see that this enzyme is roughly spherical and comprises of three polypeptide chains that are linked with disulfide bonds. 3 polypeptide chains linked with disulfide bonds. Okay, it is synthesized as a single polypeptide termed chymotrypsinogen, which is activated by proteolytic cleavage of polypeptide to yield the 3 chains. It is synthesized as a single polypeptide termed as chymotrypsinogen, which is activated by the proteolytic cleavage of polypeptide to yield the 3 chains. The active site of the chymotrypsin, marked by serine 195, lies in the cleft of the surface of the enzyme. The side chain of the serine 195 is hydrogen bonded to the imidazole ring of the histidine 75. The NH group, the N terminal of this imidazole ring, is in turn hydrogen bonded to the carboxylate group of aspartate 102. The constellation of the residues is referred to as catalytic triad. This constellation, this 3 serine 195. Now side chain of serine is hydrogen bonded to histidine 57 and the NH bonded to the imidazole ring of histidine, imidazole ring. Now this NH group of the imidazole ring in turn hydrogen bonded to aspartate 102. Okay, serine hydrogen bonded to histidine through imidazole ring, and this imidazole ring's NH portion is connected to the aspartate through H bonded to aspartate. Okay, and this constellation is known as catalytic triad. How does this arrangement of reduces lead to high reactivity of serine 195? The histidine reduces serves to position the serine side chain and to polarize its hydroxyl group so that it is ready for the depolarization. So how are they highly reactive of serine 195? The histidine residue serves to position serine. Histidine serves to position serine side chain and to polarize its hydroxy group. So that is ready for the depolarization. We'll see the structure and then we'll understand. In the presence of the substrate, the histidine residue accepts the proton from the serine 195. It will accept the proton from serine 195 hydroxy group. In doing so, the histidine acts as the general base catalyst. The withdrawal of the proton from the hydroxyl group generates an alkoid ion, okay, which is much more powerful nucleophile than the alcohol. The aspartate residue helps orient the histidine residue and make it a better proton acceptor through hydrogen bonding and electrostatic effects. So here is this. We are seeing serine connected to histidine imidazole ring, right? I don't remember. Yes, imidazole ring through the N, okay, and H, okay, and histidine is connected to the imidazole NH side through the H bonding to aspartate 102. 102? I think, okay, 102. Okay, so what are they showing is this bond is now shifted to this side and an alkoid bond is formed. So a bond is here and alkoid ion is now formed here. Okay, and now what happens? So this bond will travel here. This bond is traveling. Okay, that's all it is shown, and a positive sign is there. The catalytic triad mechanism after substrate binding step 1. The reaction begins with the oxygen atom on the side chain of the serine 195 making the nucleophilic attack, blah blah blah. This is a lot. So let us just see the diagram, what is happening. So we were there and now this is coming. This amino acid is coming, okay, and this oxygen will react with, is going to try and make a bond. Wait a second, where were we? Yeah, we should start from here. I think so. Wait a second. Yes, we should start from here. So this is the triad. What is it called? Catalytic triad. This is the catalytic triad. Okay, so this is serine, this is histamine, this is aspartate 102. I don't remember. This is this push. This ring is imidazole ring. Let me check it out again. Imidazole. Okay, I'm so sorry. Imidazole ring. Okay. So what did we see? This bond will follow through here, okay, and we'll get a plus here and we'll get dotted lines here and here, okay, and then this will get a negative sign. Didn't we get a negative sign? Negative sign, okay, and it will be making an alkaloid ion. Okay, so first step is this amino acids, peptides are coming. These are peptides, a lot of amino acids, okay, peptides, these are coming. So what is the difference? We are seeing that oxygen will see and go try to make a bond with the carbon. Okay, so we are seeing it is going here. Okay, so carbon will be like, nah, I'll have to lose a bond. Okay, these are double bonds, so if it will lose one bond, a negative sign will come here. Okay, so now this amino acid is taking away our serine. You see that serine is gone, and the H, it broke a bond here and made a bond with this. So the H will now make a bond with N. Now because N and H are here, the double bond will not be forming here because now it has 4 bonds. Okay, so that's why it is dotted and a plus sign is coming. Okay, because we have to keep it balanced. So now this is the peptide plus serine, right? And this portion now is oxyanion whole. This is tetrahedral intermediate. We have now made an intermediate. Next, what are we seeing is this N. This N now wants to make a bond with this H, right? So they are now making a bond, but let us count the number of bonds. If this is making a bond here, then we have 1, 2, 3 and 4 bonds, but N can only make 3 bonds, so it will break up with somebody else. A cleaving will come here. It will say, I'll not be with you now. So a cleavage is came and it has broken off. So the peptide has been broken in 2 parts. R1 is here with COO and R2 is here with NH. Okay, so now the acyl enzyme, what are we seeing? As soon as acyl enzyme comes, this N will break up because it had a plus, right? It had a plus, so it breaks off this also. So now there is NH and R2 bonds are satisfied, already dissolved, already cleaved, COOR1. Okay, and now we have just histidine and aspartate 102. Again, acyl enzyme, it is coming with water. So it is coming with water. What are we seeing? This aspartate and histidine, the water is reacting with the N, okay, and it is going to form a bond with water. And because it is going to form a bond with water, now we'll have lone pairs here, and these lone pairs will go and form a bond with carbon, right? So this is what we see in the next step. Again, we have COOR1OH. This is not satisfied here and here. So we see there is an oxyanion hole again. We have H here. Okay. In the next step we are seeing, so this is also negative, so this will go and bond with H. Okay, basically water has to like bond with this, H2O has to like bond with R1, and there is only, it is like this. Okay, it has to bond with this, but it will go through an enzyme, and our enzyme is aspartate 102 histidine. Okay, histidine's imidazole ring N endomere. Okay, so this is what is happening now. This will make a bond with H. Okay, and now this is satisfied. So we were because we got an H, we were back to a cation, and as soon as the H went away, okay, this bond was broken. You took a bond, so that we this negative charge came here. Okay, we made a double bond, so we broke this off, and now we have O, H, and a chain. Okay, this is serine. If you remember, this was serine. Okay, and now we have what is left, this. So we'll remove this, and we are back to the serine portion. Because with the dotted lines, we'll go with dotted lines. We're back to it. Okay, so this is what was happening. I hope I try and write this down. So mechanism, negative, whatever, oxygenal whole tetrahedral intermediate collapses and generate acyl. Oh my god. So it's so verbose, and like I don't like this. The next stage, deacylation, begins with water molecules and takes occupied, blah blah blah. I need a page. Add page. Weird. Add page. But what was that? Okay, so let us start with the thing. I don't even remember. So I need aspartate 102. I need histidine, I don't know number, and serine, and this is my, what is this, catalytic triad. Okay, let us check the numbers. 57 and 195. 57 and 195. So what does aspartate look like? Aspartate look like C O negative O, and then this. Okay, and histidine looks like H N, a pentagon with an N, double bond here and double bond here. Okay, and last but not the least, H O, and going like this. Okay, these are our three characters. Okay, now the side character or the peptide chain are 1 N H C double bond O R2, isn't it? Yeah, this is it. And one water will be coming. Okay, so let us start. First of all, we will make a catalytic triad. Aspartate, aspartate dot 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 histidine N, a pentagon dot 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 aspartate, histidine and serine. There is an H, there is an O, and okay, like this. Okay, so what is happening? Straight away we are getting peptide. Okay, peptide R1 NH C double bond O R2. We are giving it. Next step. Why can I not like write aspartate like A? Okay, because nothing is happening there, right? But we cannot, so let's just write it like this. O dot 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 H N N, and now dot 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 I'll say this and O negative, this and this, and R1 NH C double bond O R2. This will go to this. So next step we'll see. Oh my god. It's like dot 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 dot. Okay. And a positive here. This is dot 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 dot, and a positive here and a positive here, NH, and this is gone there. So R1 NH C O O R2. This will go here, and we'll see something like R N H C O minus O R2. This is what are some hole, oxidative hole, oxyanion hole. Okay, so now what is happening? Separation. Okay, after oxyanion hole. After oxyanion hole is made, we'll see again the activity of our dear enzyme. From this H, the N is coming. This N is coming to this H. Okay. R1 is with this, and when H is this, and it is separated from C. So C double bond O, one bond O, and a serine and R2. Okay, now they are separated. So next what we will see is now this is going to separate, right? So C I think this is that. Because now this N is going R1 N H and H, and this C double bond O and R2 is here. Okay, now this will get out, we'll have C and now what? This will get attracted back to, no, we are pouring water, isn't it? Yeah, you're adding water. H2O, HO, H. So is OH coming and or H coming? H is coming. Okay, always H. The rest to H is going there to the C. Okay, C double bond O, O serine R2. The H is going here and this is attacking this. Okay, now what we'll be seeing is C O negative O double bond H N pentagon N. Now again a positive here. Excuse me. And an H. Okay, and OH C double bond O dish and R2. So now this is getting overwhelmed, right? Because 1 2 3 4 5, never 5. We'll again, this is coming, so we'll go here and we'll make a negative sign and then it will go return back and we'll R2, so this will be this. Okay, so in the next step see, this is still positive and N and H is here and this is here and this whole thing, this will come down now and C double bond O, OH and O negative oxy and whole. Okay, and it is R2. This will now follow in the world. Okay, so next step will be, we have removed this. Okay, and now this will come back to our dear H C O minus O dot dot H N. Now N dot dot dot, so here is the one H O da. We are back to our enzyme and we have broken R2 here and where's the R1? Where did the R1 go? And R1 here. We have broken the peptide and this is chymotrypsin mechanism for cleavage of peptides. Yay! If tomorrow this is coming, I'm just gonna make a bloody diagram because I'm not going to write anything. Next is mechanism of lysozyme action. Lysozyme is an enzyme that destroys bacterial cell wall. It does so by hydrolyzing beta-1,4 glycosidic linkages and acetyl murmuric acid to an acetyl glucosamine, NAM2NAG. They go from NAM to NAG. To altering NAM-NAG polysaccharide component of the cell wall peptidoglycans. Lysozymes active site cleft is long enough to accommodate NAG6, which the enzyme rapidly hydrolyzes. However, the fourth NAG residues and the D ring, I don't understand this. Oh my god. So NAG, NAM, NAG, NAM, NAG, NAM, reducing end. Ouch, ouch, ouch. My god. Okay. Let us see. This is a cell wall. Okay, we have aspartate and this thing and this thing and glutamate. Oh my god, polysaccharide, substrate polysaccharide binding. We have polysaccharides here now. Okay, and we are seeing the bindings. Oh my god. And then general acid catalysis. Now polysaccharide is out with an H. Oh my god, oh my god, what is horrible. What is chemical kinetics? A plus B, C, simplest chemical, occurs in single step, A to B, A plus B plus B, unimolecular, bimolecular, termolecular, 3 molecules is rare. Rate of kinetics can be written as velocity is equal to K A substrate and B substrate concentration, right? So basis of enzyme kinetics, we see enzyme plus substrate, we make an enzyme substrate intermediate, and we give enzyme and product. Okay, includes binding enzyme and substrate, formation of enzyme substrate complex, product formation. Each step is elementary in a reaction. Importance of biochemistry: it helps understanding the enzyme mechanism of enzyme catalysis occurs through multiple elementary steps. Each step has its own rate constant. Using the derivative Michaelis-Menten equation, the classical enzyme kinetics is based on the elementary reaction. Explains formation of intermediates, transition states, activated complexes. Okay, examples in enzymology: E plus S, K1 ES, K2 E plus P, and backward is K minus 1. Okay, K1 rate constant of ES formation, K minus 1 rate constant of ES dissociation, K2 is rate constant of product formation. Okay, rate of reaction refers to the speed at which the reactant are converted to product. In biochemistry, reaction rates are extremely important because cell must produce products rapidly. Metabolic pathways depend on the controlled reaction rates. Enzyme regulates these rates. Okay, definition of reaction rates: reaction rates is defined as change in concentration of reactants and products per unit time. Okay, product substrate per unit time. Okay, negative sign for substrate decreases with time, product increases with time. Factor affecting the rates of reaction: concentration of reactants. Higher substrate concentration increases the rate reaction because more collision occurs between the molecules. A plus B, Pa. Temperature increase in temperature increase molecular motion, increase in collision increases kinetic energy, rate increases. However, for enzymes, very high temperature denatures the protein. Therefore, the enzymes have optimum temperature of 37 degrees Celsius. pH, ionization of amino acids, substrate binding, catalytic residue. Each enzyme has an optimum pH. For example, pepsin is 2 pH, pH 2, and trypsin is pH 8. Catalysis reacts increases reaction rate by lowering activation energy. Enzymes, while low speed reaction are not consumed, increases reaction rate enormously. Surface area, greater surface area, increased contact between reactants, increased rate. Important for heterogeneous reaction. Order of reaction, zero order. Definition: reaction whose independent of the substrate concentration. Rate equation: V is equal to K. Okay, we are not doing all this. Okay, for half-life, I don't think the questions will come from this. Okay, biological invariant, phosphate, V is equal to K on substrate A. Integration 0.693 upon K, T half. Okay, second order, it's not important right now. Transition state, this is the transition state. Transition state theory states that the rate of reaction depends on the number of molecules that can achieve the transition state. Higher activation is reduced and visually. In an catalyzed reaction, activation energy is 5. Fewer molecules reach transition state. Increase reaction proceeds slowly. In enzyme catalyzed, EA is lower. Transition state is formed easily. Reaction proceeds rapidly. Reactants. When substrate binds to an enzyme, the enzyme reduces structural changes. This distorts the substrate bond and pushes the substrate forward to the transition state configuration. This phenomenon is known as transition state stabilization. By stabilizing the transition state, the enzyme lowers the activation energy needed for the product formation. For example, many enzyme substrate for example, in many enzymatic reactions, substrate molecules are strained, bonds become weakened, charges are stabilized. All these help in stabilization of whatever. Properties, not important right now. No, we're not doing this. We are not doing this. Yeah, we are doing this. Michaelis-Menten. So, our dear Michaelis-Menten. Here we are. Michaelis-Menten equation is the fundamental equation of chemical kinetics. It describes the relationship between the enzyme catalyzed reaction and the substrate concentration. This equation was proposed by Leonard Michaelis and Maud Menten in 1913. It remains one of the most important concepts in chemistry. It explains how enzyme behaves in different substrate concentration and forms the basis of understanding of enzyme activity, catalytic efficiency, and enzyme inhibition. So this is the concentration of substrate and this is time. As time goes, the substrate concentration is increasing. What is this? What is this? Anyways, what we are seeing here is Michaelis-Menten models that the first enzyme first binds with the substrate and its temporary enzyme substrate complex and then breaks and products and release enzyme unchanged, represented by this. Okay, the basis suggests the enzyme do not directly convert substrate into product. Okay, and then it is first bind to the active site of enzyme and ES complex. ES complex is intermediate and dissociates back to the enzyme and substrate and or proceeds forward to product. Menten and Michaelis observed that when substrate concentration is increased, the reaction velocity increases. So substrate increases, velocity increases, but eventually reaches the maximum value beyond which the further increase in substrate does not increase. Okay, Vmax तक ही जाएगा. This occurs because the high substrate concentration, all enzyme active sites become occupied. Relative velocity and okay, V is equal to Vmax to substrate upon Km plus substrate. Okay, Michaelis constant. Meaning of Vmax represented the maximum velocity achieved by the reaction of the enzyme fully saturated with substrate. At this point, all active sites are occupied. Increasing substrate concentration further does not increase reaction rate. Okay. Vmax depends on enzyme concentration, catalytic efficiency of the enzyme. A higher enzyme concentration produces higher Vmax. Meaning of Km. What is Km? Michaelis constant. What is Michaelis constant? Is one of the most important parameters of enzyme kinetics, defined as the substrate concentration at which the reaction velocity becomes half of Vmax. Okay. So we are seeing here rate. We are seeing here concentrations, substrate concentrations. Okay, so this is Vmax. So here is Vmax by 2. So what we see, the concentration at which the rate is Vmax by 2 is called Km. the constant at which the reaction velocity becomes half of Vmax. Okay. So what are the significances of Vmax? Low Vmax, what the significances of Km? Low Km, high substrate affinity. Okay, Km is low, so there is high substrate affinity. So say this is two different reactions. So first Km is this and second Km is this. So this is the lower Km. So this shows it has this reaction will have high substrate affinity. Okay. The enzyme binds substrate strongly. Okay. The small amount of substrate is needed. Okay. So and this one is showing low substrate affinity, weaker binding, and more substrate is required. Wow. Km is inversely related to the substrate affinity. Substrate affinity Km is inversely proportional to substrate affinity. Behavior of different substrate concentration, Nicholas maintenance explain blah blah blah. So if substrate is very small, then Km plus summation this is equal to Km. What is this? This is this velocity. Okay. V is equal to Vmax into substrate upon Km plus substrate. Vmax into substrate upon Km plus substrate. This is y-axis cross x-axis. This is x-axis cross x-axis. Okay, x-axis plus x-axis. Oh my god, remember this. Okay, Vmax times substrate concentration upon Km plus substrate concentration at that given point will give the velocity of that given concentration of the substrate. Okay, this will and this will remain constant. Under these condition they will remain constant for a given chart, right? For a given enzyme, blah blah blah. Under these conditions, reaction velocity is directly proportional to substrate. We are saying V is directly proportional to substrate. When substrate given, if this is Km and substrate is very less than, at this point, what is the speed? So we are saying the velocity is directly proportional to substrate concentration. The reaction follows first order kinetics thus. Okay. And now in this one we are seeing the concentration Km is here and the substrate concentration is very high. So now we are saying that Km plus S is equal to S only. So this means V is equal to Vmax substrate Km plus substrate. Now we are saying this is equal to S substrate only. So this will cancel out with this. So velocity is equal to Vmax. Okay, because Vmax. This is something like this. Enzyme becomes saturated, reaction rate becomes independent of the substrate, and it is a zero order kinetics. Assumption of the Michelson-Menten. We are seeing the formation of enzyme substrate product. I don't want to read this. Okay, formation, derivation. So important. Okay, derivation of Michelson-Menten reaction. So from this we have three rates. R is equal to K1 substrate and substrate. Okay, reactant product. Okay, next breakdown of ES, the backward reaction. R is equal to K minus 1 ES. Next is R is equal to this formation for K2 ES. Okay, so we'll see what we are seeing: breakdown of ES and formation of ES. Okay, so total formation is this and total breakdown is this. So how we'll add this up: K minus 1 ES plus K2 ES. Okay, so K minus 1 plus K2 ES. What we are seeing next is rate of formation is equal to rate of breakdown. So we have K1 ES is equal to K minus 1 plus K2 E and S. Okay, so we'll take K's one side and substrate and products one side. Okay, so now that we have taken, like, what do we want? Okay, so we are taking this here, substrate upon transition state is equal to K minus 1 plus K2 upon K1. So we are seeing this is equal to Km. Okay, Km is Michaelis constant. Now that we have Michaelis constant. Okay, next is express free energy concentration, free enzyme concentration. So we know enzyme total is equal to the enzyme we have plus what is in the transition state. Okay, so enzyme we got left plus is equal to enzyme total minus enzyme of transition state, right? We have this, and Km is equal to this one, ES upon ES, transition state, ES upon transition state, ES. Okay, so we'll put this here, ED minus ES upon ES, and this is substrate. So next we have, what do we have here? This is Km. I don't understand what did they do here. Let me just do simple things. Okay, wow. Km is equal to ET minus ES upon ES times S ES. Fine. Sorry. Okay, next step is ET minus ES okay, still whole multiplied by this, or I can just say Km upon substrate. Why take so much pressure? Okay, so this is cancelled out, and now we have ET minus 1, okay, upon, sorry, yes, this is not looking cool. Let me try it again. So Km Es upon S is equal to Et minus Es. I want this Et and Es together. Let's just try it. Km Es is equal to Et substrate minus Es substrate. The same. Now I have Km is equal to Et substrate upon Es minus Es substrate upon Es. This is cancelling out and I am left with an S. Okay. That S can go there. Not getting it. Et S minus S. How are they doing this? What black magic is that? Huh? Fifth step, am I shitting? Oh god. It is saying solve for ES, right? I'm gonna solve it for ES. ES, this is for you. I am taking ES here, and now Et minus ES is here with came down here. I don't understand. Okay, dear ChatGPT, it's your turn. The ChatGPT. Derive the Michaelis-Menten reaction. What did I just say? Oh god, I'm horrible. Beautiful ChatGPT, beautiful. Can you show me step 4 stepwise? Can you give me step 4? Like, explain me the step 4. ChatGPT. ChatGPT. It's not working. Why is not anything working today, huh? The unknown free enzyme concentration ES is equal to transient state is equal to substrate and enzyme product upon K. What? Where did this come from? Okay. Oh my god. This is like the first step. Oh my god. Oh my god. Okay. E with ET in. We have now, what do we have? KMES is equal to ET ESS KM so KM intermediate ET minus intermediate substrate